My name is Dootika Vats. I am at the Indian Institute of Technology, Kanpur in India. It would have been lovely to attend MCQMC in person and be at Oxford around this time, but unfortunately, we can't really be there. Um, I will be talking about lug-sale lag windows for estimating time average covariance matrices. As I move along in the talk, I will explain what lag windows are and what time average covariance matrices are. What a lug-sale is exactly this particular thing over here. So this shape is going to be important to keep in mind as we go along. If you have watched this video as part of the continuum of lectures as part of this mini symposium. Then right before my talk is James Fliegel's talk, who's also a collaborator on this project, and he's spoken about output analysis, and that probably sets up a lot of the problems that we're going to discuss today, but I will repeat them nonetheless. All right, so jumping right into it. The first thing I wanted to discuss was what are exactly time average covariance matrices, because they're known as different things in different fields. So suppose YT is a covariant stationary process. Then in many applications, a critical quantity of interest is this infinite sum of lag covariance matrices. So this is going to be a P by P covariance matrix. And so I'm interested in estimating sigma, which is the infinite sum of these P by P covariance matrices. And sigma pops up as different things in different fields. In a steady state simulation and MCMC, we call this time average covariance matrix. We call sigma the long run covariance in econometrics and in general in time series. It's also called Monte Carlo covariance or limiting covariance in MCMC particularly. We will focus our attention on MCMC here also, mainly because of the particular challenges that MCMC has with respect to the size of the data that it generates. So we will focus our attention on MCMC here, but whatever we discuss is actually applicable to all 3 or 4 areas here. Okay, so in MCMC particularly, I'm going to set up the notation so that we can understand the exact problem of interest for us. So pi is our intractable distribution that's defined on some space, and just to be clear, we're calling that script x. And there's some p-dimensional function g whose expectation is of interest to us. So of course, we're also assuming that this expectation is finite. And this returns expectation of g under pi is a p-dimensional vector, and we want to estimate this. In MCMC, a pi-ergodic Markov chain xt is constructed. And of course, there's a lot of details out there on how to construct such a chain. We're not really going to talk about much of that. But if I call yt be the transform process, so g or xt is going to be yt, then I can estimate the expectation of g under pi with the Monte Carlo average, g bar n, which is just the average of all the samples obtained up until a time point n. And this, of course, also is a p-dimensional vector. If I get a large number of samples, and I let the number of samples go to infinity, then the limiting variance of g bar n is exactly sigma, which we've defined previously. Again, nothing but the infinite sum of the covariances of y1 to y1 plus k, where these k's are the lags. And that I'm going to denote as rk. So the lag k covariance matrix is going to be rk. And I'm summing that over k going from negative infinity to infinity. So now a critical problem is that we want to estimate sigma, because if we can estimate sigma, then we can summarize the variability in g bar n, because as n increases, g bar n does go to the truth, the expectation of g under pi, but sigma allows us to estimate the variability in g bar n. A very common and popular estimator is the spectral variance estimator, and it's somewhat easy to motivate. So because sigma takes up the infinite sum of these rk's, let r hat k be the lag k sample covariance matrix. Right? That's just the usual form. And then what we can do is we can estimate sigma, which is the infinite sum of rk's, with sigma, which is the sum of r hat k's weighted by some weight function W. So this is a weight function, and then truncated at some B, because we don't really have infinite samples available to us because we're observing YT, our process, at some finite points. So we do have to truncate somewhere, and so we truncate at some B. Right? So B is our, like I said, our lag truncation point, and then Wn is the lag window. And a common condition is that the lag window or weight function Wn is less than equal to 1. Right? This is not necessary, but it's often what is chosen. The weight functions that are chosen, the lag windows that are chosen, are always less than equal to 1. And what happens as a consequence of these two conditions is that because I am truncating this infinite sum at some B, that introduces some underestimation, particularly when Rk is positive. Right? So we're focusing our attention a little bit in MCMC, where positive correlations are customary. So when you truncate an infinite sum at a certain point, we're leaving out some extra information, and that extra information is lost, which leads to underestimation. And Wn, because we're weighting and it's less than equal to 1, this weight function, that also brings in an underestimation. So overall, we get that this spectral variance estimator sigma hat, in general, underestimates sigma. Although it has nice asymptotic properties, in finite samples, it underestimates sigma. This underestimation is particularly pertinent for highly correlated processes, because as we truncate at some point B, whatever's left after B is actually more substantial for highly correlated processes. And similarly for the weight function as well. So what we would like to do is we introduce these Lug-Sale lag windows that are specifically constructed to allow the weight function to be more than 1 for some lags. Okay? And because that weight function is more than 1, it actually gives it some extra weightage and pushes estimation that's not underestimation, but in fact overestimation in large enough samples. And I'll describe that more theoretically later. So some common lag windows that are used are the Bartlett lag window, which is this particular linear lag window. The Tukey-Hanning lag window, which has this nice cosine type behavior. And then the QS, or the quadratic spectral lag window, which is a little bit different because it doesn't necessarily truncate. And you can write up a similar setup for the QS lag window as well. But these are the three common lag windows. And if you notice, all three of them max at 1. So on the y-axis, they don't necessarily go above 1. So there is a cap and upper bound over here. Okay. And in the Lug-Sale family of lag windows, our fix is quite simple, actually. What we want to do, or in fact we do, is that for some parameters R and C, and I'll explain them in a bit, Lug-Sale lag windows are just a linear combination of the following. So Lug-Sale lag window is defined as W sup L, and that's a linear combination with weights 1 over 1 minus C and C over 1 minus C. Of the original lag window over here, and another lag window over here that basically scales the x-axis by a factor of r. Right? And what that does, if it's difficult to see just by the formula, what that does is the following. If you look at the three original lag windows over here, so this is not Lug-Sale, but if we pick up, for example, the Bartlett lag window, which is linear, then I map that over here. This is the usual R equals 1 structure. So when R equals 1 over here, when this is 1, then this just goes away and it becomes the usual lag window. But when R equals 2, then we get something called the Flattop lag window. So it's flat over here. That means the weights are exactly 1 for up until a certain time, and then it reduces linearly downwards. But when R equals 3 and C equals a half, we get this upwards behavior that looks like that Lug-Sale in the first on the first slide, and so that's where the name comes from. Similarly, for the Tukey-Hanning lag window, we can look at what R equals 1 does, which is the standard lag window. And then we can look at, for example, R equals 2 and C equals 1 over 4, and that brings in a slight, so it doesn't make it go above 1, but it slightly flattens it out. But if I set r equals 3 and c equals 1 over 5, it actually increases that over here a little bit. So if I draw a line over here at, at 1, we can see it kind of uplifts it slightly above 1 in an effort to overweight the covariance and covariances, and similarly for the QS lag window as well. Right? So this is a small little fix, and what it does is that it introduces large sample positive bias as opposed to large sample negative bias, which is caused by the underestimation, the truncation, and the weighting below 1. So all we need to do now is take our lug-sale lag windows and put them in our spectral variance estimators. So we can construct the same spectral variance estimator, which has this r hat k and this truncated sum, but instead of the usual lag window, we'll just put in the lug-sale lag window over here, right? And that should be it. We can actually show really nice properties. You still have the nice asymptotic properties of strong consistency, but what we get is that for large enough n, this actually exhibits positive bias as opposed to negative bias, but is still asymptotically unbiased and mean square consistent and all of the nice properties. And I can go on to talk about that further, but there's a little bit of a problem. It's actually just too slow for large n and p. And this is not just a problem with lug-sale spectral variance estimators, but just the class of spectral variance estimators in general. So it's actually not very good for MCMC, where typically a typical size of MCMC output can be in hundreds of thousands up to millions, and p could also very easily be high dimensional. So essentially what it means is that if we were to use sigma in our output analysis steps to try and assess what the variability of G bar n is, to use spectral variance estimator means to give away a significant amount of time that we could have used in just getting more samples. And we want to avoid that. We want to find an estimator that's actually fast. Right? An estimator that we know is fast is the batch means estimator. So I'll take a few minutes to explain that here. So the batch means estimator does is it takes your sample size n and it breaks it up into a number of batches, each batch of size b. And so if I look at y1 through yb and yb plus 1 through y2b and the last bit of b's, and I look at the average vector within each batch, those are my y bars going from y bar 1 to y bar a. So those are a batch mean vectors. And now if I just look at the sample covariance matrix of those y bar k's, scale it appropriately by b on the outside, then that gives me my batch means estimator. Okay, and this estimates sigma, and there's a rich amount of literature on nice properties, nice asymptotic properties of this estimator. The good news is that it's fast. It's quite fast. The bad news is that this also is biased from below. In a very similar way that the spectral variance estimator is biased from below. And essentially, part of the intuition is that we're only considering batches up to b and not beyond from b up until n. That's one source of bias, for example. We would like to use a similar trick of using a lag window and giving extra weights so that we can inflate the bias artificially in some sense. But there's no lag window actually present here. There's no Wn in the formula for batch mean, so we don't really know how to introduce that. So that's a little bit tricky. Luckily, there's a nice little work by Ying Lu and James Flegel as well, where they consider these class of weighted batch means estimators. So these are fairly complicated to write down. So I've written them out in gray over here, but don't focus too much on them if they look just slightly too intimidating right now. But essentially what they say is if you consider the class of weighted batch means estimators, which have lag windows in them, and you put in a Bartlett lag window, then you get nothing but the batch means estimators back. So if I just sneak into the gray area a little bit, there's this lag window over here in the form of this delta 2 of the lag windows. And if I just introduce the Bartlett lag window here, then that's going to just give me the batch means estimator back. Okay, and that's it. That's all I'm going to talk about are the weighted batch means estimator. But the key idea is you can go to these weighted batch means estimators and put a linear lag window in to get something akin to the batch means estimator back. And as it turns out, if we use a Lug-Sale-Bartlett lag window, so just the Bartlett lag window, but the linear combination, then we get our Lug-Sale-BM estimator, which is nothing but a linear combination of batch means estimators, one with batch size B and the other with batch size B over R, where R, remember, is a parameter that essentially tells you how high do you want to go above 1. So this estimator actually is still fast because this is just 2 calls to a batch means estimator, and we'll show in the next few slides that it can also yield positive large sample bias with good choices of R. So for these set of results, it's just easy to write the results down with C equals half because then the bias and variance results are not too messy to write down. But of course, the results apply a lot more generally. So the first is the bias result. So if we assume that the right number of moments exist, which is standard, and we assume that the Markov chain is polynomially ergodic, then I can write down that the bias of the Lug-Sale batch means estimator is R minus 2. So that's the term coming from the choice of R times this particular quantity over here. Okay, and so in the numerator you have a summation. That's an infinite sum over k of k times the lag covariance matrix Rk plus Rk transpose. Plus you also have a small order bias term that is typically, in fact, typically negative. So if we just delve into this a little bit, if I set R equals 1, which should give me back the regular batch means estimator, then what I get is a negative sign over here plus, negative sign times an infinite sum of k times the lag covariances divided by b. And this is the typical underestimation that we witness when we implement a batch means estimator. So it's this particular negative summation over here, negative bias term over here, plus a second order negative bias term that comes from the second order term. When I use R equals 2, then I don't have the first order term, but for small choices of B and N, I actually do have this second order bias term over here that can be fairly significant. And so if I actually choose R equals 3, then what I get is the same term as the batch means estimator, except it is no longer negative, right? So there's no negative sign. It's actually the exact bias has been offset in the positive direction. Okay, so using R equals 3 allows us to enforce a positive large sample bias using this Lug-Sale family of batch means estimators. Okay. Of course, we introduce a positive bias, but we need to make sure that the estimator of the variance itself is stable enough. That is to say that its variance does not blow up in any unreasonable way. So again, under similar conditions, and there's slightly more technical conditions that ensure things are finite, for example, we have a result that says essentially that the variance of the Lug-Sale batch means estimator is this usual, this variance expression over here, that's a function of the truth times a multiplicative factor, that's a function of R. And as R increases, this variance increases. So if you look at the variance of batch means with R equals 2 and variance of batch means with R equals 3, this is approximately just about less than 1. So as R increases, we're going to lose out on some level of estimation quality, but it's worth it, especially for highly correlated processes, to overcorrect for that negative bias, as we'll show in our examples, which we come to now. So consider the Bayesian logistic regression example. This is quite stereotypical. There's other examples in the paper as well. So we have the cardiovascular study data from Framingham, Massachusetts in the United States. So this is a study that's been going on for many years, and they've collected many different things as part of this study. The particular quantity or quality we're interested in is a response variable, which indicates whether a patient has a 10-year risk of coronary heart disease or not. And there's some set of covariates that you can find in the paper, but I haven't elaborated them here. Essentially, there are 18 covariates, including intercept. And if I let beta be the regression coefficient, consider a logistic regression setup. This is an expression of the likelihood over here. And we assign a multivariate normal prior on the betas. The resulting posterior is intractable, but we can use the MCMC pack library in R to sample from this posterior distribution. And just so we're clear, we're interested in estimating the posterior mean of beta, which means that our G function is just identity over here. So in order to compare the performance of the time average covariance matrix estimators, what we'll do is we'll run this Markov chain for a really long time and get a sense of what the true posterior mean of beta is. And then in repeated simulations, check how many confidence regions around the estimate of the posterior means using each of the Lug-Sale methods gives us the best coverage. Right? And so that leads us to coverage probabilities using batch means with R equals 1. So that's this thing over here. This is with R equals 2, and this is with R equals 3. Right? So remember, R equals 3 gives us this Lug-Sale effect. R equals 2 gives us this effect, and R equals 1 is this Lug-Sale effect over, sorry, this batch means effect over here. And we do this for different values of n. So 1,000, 50,000, and 100,000. And because we're making 90% nominal confidence regions, we would like to be at 90% coverage eventually, but we see that in finite samples, batch means with R equals 3, or the Lug-Sale batch means, is giving us about 62% coverage as opposed to 36% for using R equals 1, the traditional just batch means estimator, and 47% using R equals 2, which is zero first order bias, but a smaller order bias that is usually negative, and that brings the coverage down. And so early on, we inflate the coverage, and as the sample size increases, the coverage probabilities slowly improve for all of them, but for Lug-Sale, we're closest to 90%. Okay, and this has a big impact, particularly on when we terminate our MCMC simulation. So we'll see that in the next slide. So one common way of terminating MCMC is using effective sample size. So our idea is to now plot estimated effective sample size divided by n. And the idea is that since ESS is used to terminate simulation often, we want to see what is going to be the evolution of effective sample size as n increases. If we overestimate ESS, then that will imply that we will likely terminate simulation too early, or earlier than we'd be comfortable with. And so overestimating estimating ESS leads to false early termination. And if I plot the evolution of the effective sample size for R equals 1, 2, and 3, this blue line is R equals 3 over here, and that converges from below, right? So we see that it starts over here and then essentially converges from below. That means it's actually underestimating the effective sample size early on in the simulation, and then converging closer and closer to the true effective sample size. Whereas R equals 1 and R equals 2 overestimate the ESS, leading the user to possibly be exposed to terminating their simulation way too early. Okay? And so this is the impact of the Lug-Sale estimator of sigma, is that you safeguard yourself against early termination, something that is often an issue, especially in highly correlated setups. Right. So some final remarks, and I indicated this in the very first slide. This is not restricted to MCMC. It can be applied to HEC matrices estimation, particularly in econometrics, and in many steady state simulation examples and setups. Of course, we focus on MCMC because MCMC requires the estimators to be fast, and so that's one of our motivations. Which means we've also actually coded this fast implementation in the R package MCMC SE, which is available on CRAN and on GitHub. There are, in addition to the large sample bias and variance results, there's also strong consistency that's available to us for as long as R is greater than or equal to 1. There's some issues with making sure that the estimator of sigma is in fact positive definite, and so we've proposed corrections for positive definiteness as well, so that sort of keeps things in check. And finally, the performance of all of these time average covariance matrices depend on the truncation point or the batch size selection B, and that's actually critical to the performance of what's going on. Now, keeping batch size constant, whatever it is, log sale lag windows appear to be doing significantly better in making sure you don't terminate too early, especially for MCMC. But it would be really useful to go in and say, okay, what is a reasonable batch size selection procedure in these family of problems? And that's ongoing work. Well, thank you again. If you have any questions, because we don't really have a question answer round, but if you have any questions, I'm happy to answer them over email. There's an archive version of the paper available. And again, feel free to email me if you have any questions. Thank you again.